can draw a Bode plot for a system whose open loop transfer function is given to us. So let's take a problem. So our problem is to construct the Bode plot on a semi-log graph sheet for a unity feedback system whose open loop transfer function is given to us as GS equals to 50 upon S 1 plus S and 1 plus 0.5 S. So this is the open loop transfer function of the system. And after constructing the Bode plot, also we have to check the stability of the closed loop system. Okay. So let's try to solve this problem. So the first step to construct the Bode plot is to put S equals to j omega, that is convert this transfer function in the frequency domain. So step number 1 is to put S equals to j omega in the transfer function. So it will become gj omega 50 upon j omega 1 plus j omega and 1 plus 0.5 j omega. Okay, so this is the transfer function in the frequency domain. Now step number 2 is to calculate the magnitude and phase angle of this gj omega. So step 2 is to calculate the magnitude. Magnitude is m gj omega magnitude. So let's find the magnitude of it. If we take this gj omega, then it is 50 upon j omega 1 plus j omega 1 plus 0.5 j omega. So magnitude of this constant term 50 will be 20 log 50. Then we have j omega, so its magnitude will be 20 log j omega. Then we have this minus sign is because we are now taking the magnitude of the denominator terms. Here we have minus 20 log 1 plus j omega. Then we have minus 20 log 1 plus 0.5 j omega. So this is the equation for the magnitude. Mark it as 1. Now calculate, solve it so that we can simplify this equation. 20 log 50 calculated, it will come out to be 34. Then we have minus 20 log omega minus 20 log under root of, here we are taking the magnitude, so magnitude will be 1 plus omega square. Here the magnitude will be under root of omega square, so it will be omega. because j omega, it is a complex term, so if we take its magnitude, then it will be square of the real part plus square of the imaginary part. Like if we are having x plus jy, then its magnitude will be under root of x square plus y square. Here we have j omega, so its magnitude will be under root of 0 plus omega square. So omega we have written here. Now here the magnitude will be minus 20 log. This will be 1 plus 0.5 omega square. So under root of 1 plus 0.5 omega square. So this is the magnitude expression. Now taking the phase angle. So phase angle is represented by phi. So phi will be tan inverse of 0 upon 50, because here we are having no imaginary term, only real part is present. So for this like x plus jy, the magnitude phase angle will be tan inverse of y by x. So here for the constant term 50, we will be having phase angle as tan inverse of 0 upon 50. Then for this omega term j omega, we will have minus tan inverse of omega upon 0. Then we have minus tan inverse of omega upon 1. Then minus tan inverse of 0.5 omega by 1. Here real part is 1, imaginary part is omega, so it will be tan inverse of omega upon 1. Here we will have tan inverse of 0.5 omega upon 1, and for this we have tan inverse of omega upon 0, because real part is 0. So this is how we calculate the phase angle of this transfer function. We have got the magnitude and we have got the phase angle. Okay, now make a table so that here we will it will be easy for us to plot this magnitude and phase angle with respect to frequency we have to plot. So let's form a table for the magnitude plot. This is the factor, this is the corner frequency, it is the slope, and then we will make a column for the remark. So first factor we are having as the constant term, and constant term is 50. In the magnitude equation you can see that the first term is constant term is 50 and its magnitude is 20 log 50. So first factor is 50, its magnitude is 20 log 50, and it is value, it is coming out to be 34 dBs. Okay. Corner frequency, because for constant term we have no corner frequency, so corner frequency is none. Slope for the constant term is 0, so it is 0 dBs per decade. And what we will write in the remark, that how we can represent this constant term in the magnitude plot. This constant term will be represented by a straight line having no slope, and this straight line, it will start from this 34 dBs and it will be parallel to the 0 dBs line. So let's form the table for the magnitude plot. So the first factor in the magnitude equation is the constant term. In the transfer function we have the constant term as 50. So first factor is the constant term 50, and the magnitude of this constant term 50 will be given by 20 log 50. And when we calculate this 20 log 50, it will come out to be 34 dBs. Okay, so this is the magnitude of this constant factor 50. Corner frequency associated with this factor will be 0. So here we will write none, because the constant term will have no corner frequency with it. Now slope will also be 0. 0 dBs per decade will be the slope, and this constant term 50, it will be represented on the Bode plot by a straight line of slope 0 dBs per second, 0 dBs per decade, and it will start from 34 dBs point. Okay, so this is how we are going to represent this constant term 50 on the Bode plot. So it was the first factor present in the transfer function. Now second factor is 1 by s, and the magnitude of this 1 by s will be minus 20 log omega. Okay, and corner frequency will be 0, no corner frequency, and the slope will be minus 20 dBs per decade. Okay, and how we can represent this 1 by s on the Bode plot? It will be a straight line of slope minus 20 dB per decade, passing through omega equals to 1. Okay, this will be a straight line. The slope of the straight line will be minus 20 dBs per decade, and this straight line will pass through the point omega equals to 1. So this was the second factor. Third factor is 1 upon 1 plus s. It can be written as 1 upon 1 plus j omega, and its magnitude will be minus 20 log under root of 1 plus omega square. Okay, here constant, here real part is 1 and imaginary part is s, that is j omega. So the under root of real part plus the imaginary part square, so 1 plus omega square, so minus 20 log under root of 1 plus omega square. The corner frequency can be calculated by the coefficient of omega. So coefficient of omega here is 1, so corner frequency is 1. Now slope will be minus 20 dBs per decade, because here the power of this 1 plus s is 1, so the slope will be minus 20 dB per decade. If it is, the power will be 2, so here the slope will be minus 40 dBs per decade. Okay, how we can represent this? This will also be a straight line of slope minus 20 dBs per decade, and starting from omega equals to 1. It will start from the corner frequency point. So corner frequency is omega equals to 1, so it will start from that point. Now fourth factor is 1 upon 1 plus 0.5 s. Okay, this is our fourth factor. So its magnitude will be minus 20 log under root of 1 plus 0.5 omega whole square. Okay, 0.5 omega square and 1 plus here. Corner frequency will be 1 upon 0.5, that is 2. Okay, and slope will be minus 20 dBs per decade. How we can represent this on the board plot? This will again be a straight line of slope minus 20 dBs per decade and will start from the point of the corner frequency. So here corner frequency is 2. So this straight line will start from omega equals to 2. So it will be a straight line. Of slope minus 20 dB per decade starting from omega equals to 2. So we have considered all the four factors present in the transfer function and we have find out the corner frequency, slope, magnitude and how we can represent these factors on the board plot, that is for the magnitude plot. Now we have to again form a table for the phase plot. Okay, how we can represent all the factors on the phase plot. So let's form the table for the phase plot. So now for the phase plot we will use the phase equation, that is phi equals to tan inverse of 0 upon 50 minus tan inverse of omega upon 0 minus tan inverse of omega upon 1 minus tan inverse of 0.5 omega upon 1. Now this will become tan inverse of infinity, so it will be minus 90 degrees. Here tan inverse of infinity, it will be tan inverse of 0. So it will be 0, it will be 90 degrees. So minus 90 minus tan inverse of omega minus tan inverse of 0.5 omega will be our phase equation. Now in this phase equation, that is we are going to put various values of omega, and for those values of omega we are going to find out the value of phi. Okay, so let's take different values of omega, like omega equals to 0. Put here omega equals to 0, so it will be tan inverse of 0 minus tan inverse of 0. So tan inverse of 0 is 0 degrees, so the phase angle will be minus 90 degrees. Now take another value of omega like 0.1. So it will be minus 90 degree minus tan inverse of 0.1 minus tan inverse of 0.5 into 0.1. Okay. So here when we calculate the value of phi, it will come out to be minus 98.6 degrees. Again take another value like 0.5. So here minus 90 degree minus tan inverse of 0.5 minus tan inverse of 0.5 into 0.5. Okay, so 0.25. So here the value of phi will come out to be minus 130.6 degrees. Similarly, take different values like 1, 1.4, 1.5, 2, 4.45. Okay. Now for omega equals to 1, here tan inverse of 1 minus tan inverse of 0.5, okay, into 1. So it will be tan inverse of 0.5, tan inverse of 1 will be 45 degrees. So minus 90 minus 45 minus tan inverse of 0.5. So the phi angle, it will come out to be minus 161.6. And similarly, we will calculate the value of phi for different values of omega. So it will come out to be minus 179.5 degrees, minus 183.2, minus 198.4 degrees, minus 233 degrees. So here we have calculated the different values of phi for different values of omega, okay, using this phase equation. So we have the table for the phase plot, and also we have the table for the magnitude plot. So let's draw the Bode plot for this problem. So this, whenever we want to draw the Bode plot is drawn on a semi-log graph. So this is a semi-log graph, and on this we are going to draw the Bode plot. Now Bode plot, it consists of two plots, the magnitude plot and the phase plot. So magnitude plot, for magnitude, on the left hand side we are going to choose the magnitude scale, taking the magnitudes like 0 dBs, 10 dBs, 20 dBs, and in negative also like minus 10, minus 20, minus 30. So this shows the magnitude of the transfer function factors. Okay, so here we have magnitude in dBs on the left hand side, and on the right hand side we are going to mark the phase angles in degrees, like 0 degrees, minus 90, minus 180. So this is for the phase plot. This scale will be used for the magnitude plot, and right hand side scale will be used for the phase plot. On the x-axis, we are going to mark the frequencies, and because it is a semi-log graph, so here the frequencies will be changed in decades, like in the factors of 10. So here the frequency is marked like 10 raised to the power minus 1. This is 10 raised to the power 0. It is 10 raised to the power 1, 10 raised to the power 2, like 10, 100, 1000, 10,000. So in this way, this denotes the decades. So whenever we mark, you have seen that the slope in the magnitude plot, it is shown as dBs per decade. So this per decade term, it is used because here in semi-log graph, the factors, they are changing in the power of 10. Okay, so by 100 they are changing, so that's why we are using per decade term. Now we have a scale here. We can choose the scale according to the question. Here it is given 0, that is 0 dBs, minus 10, minus 20, minus 30, minus 40. It is being shown in negative, and here 0, 10, 20, 30, 40. Okay, so here we will choose the scale like minus 20 we have chosen here as 0 dBs. So mark it as 0 dBs. This will be 10 dBs, 20, 30, 40, 50, 60. It is in positive, and here it will be negative like minus 10, minus 20, minus 30, minus 40, minus 50. In this way, that we can change the magnitude scale according to the question. Okay. Here we have the phase angle scale. Now mark the 0 dB line here. This is the 0 dB line. Because with respect to the 0 dB line, we are going to draw all the factors. And for phase angle, we will mark this minus 180 degrees line. So first upper part is for the magnitude part, and lower part is for the phase plot. Okay, this is minus 180 degrees, and here it is 0 dBs. Now let's start drawing the magnitude plot. For magnitude, we have the table like this. Okay, and the first factor 50, that is the constant term, it was having the magnitude 34 dBs. Okay, and it will be represented on the Bode plot by a straight line which is having slope 0 dBs, and it will start from the point 34 dBs. Slope is 0, that means it will be a line parallel to the 0 dBs line, and it will start from the point 34 dBs. So mark this line on the magnitude plot. It will be 34 dBs magnitude, start from the 34. So this is 30. So 31, 32, 33, 34. It will be in the middle of, somewhat like middle in between 30 and 40s. So it will start here and it will be a line parallel to the 0 dBs line having no slope. So this is what? 34 dBs. Okay, 34 dBs line. Okay, we have represented the constant factor 50. Now second factor is 1 by s, and its magnitude is minus 20 log omega, and it is having slope minus 20 dBs per decade. It will be a straight line of slope minus 20 dBs per decade passing through omega equals to 1, and it will be starting from the point minus 20 log omega. Okay, so let's draw this line. 20 is here, so it will start from 20. Mark the frequency omega equals to 1. This x-axis, it is showing the frequency. So we will choose the scale according to our requirement of the question. Mark this as 0.1. This is 10 raised to the power minus 1. So 1 upon 10, it will be 0.1 here. Then we have 1 point, this is 10. So here we have omega equals to 1. This is 10. This is 10 raised to the power 2. So at omega equals to 1, this straight line is going to pass from here having minus 20 dBs per decade. Minus 20 means negative slope. Okay, this is how we are going to represent the factor 1 by s. Write the slope term over this line, minus 20 dB per decade. This is omega equals to 1. Here the slope is 0 dBs per decade and magnitude is 34 dBs. Now third factor we have as 1 upon 1 by 1 plus s. Its corner frequency is omega equals to 1. So it is going to start from the point omega equals to 1 having the slope minus 20 dBs per decade. Straight line of slope minus 20 starting from omega equals to 1. So this is omega equals to 1. Okay, and its slope is minus 20 dBs per decade. So this is going to be minus 20 dB per decade. Due to this term, this line is also passing through omega equals to 1, and this line is also going to pass from minus 20. So this straight line is representing both these factors. This was due to 1 by s, and this is due to 1 by s plus 1 upon s plus 1 plus s. It is due to both these factors. Okay. Now we have fourth factor as 1 upon 1 plus 0.5 s, and its corner frequency is 2. So this will be going to a straight line having the slope minus 20 dBs per decade and starting from the frequency omega equals to 2. So mark the frequency omega equals to 2. It is 10. It is 1 and it is 10. So 2 will be here. This square. 1, 2, 3, 4, 5, just like this. 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be omega equals to 2. So from here we are going to draw a line having a slope minus 20 dBs per decade. Due to the factor 1 upon 1 plus 0.5 s. This line will go here in this way also, but here I am not drawing it because it will you get confused here. So we have represented all the four factors. First factor is the constant term 50. Second factor is 1 by s, having this straight line represented by this straight line passing through omega equals to 1 and starting from this 20 dBs. Okay, and again we have a straight line due to this factor 1 upon 1 plus s starting from omega equals to 1, having the slope minus 20 dBs per decade. Here we have the fourth factor minus 1 upon 1 plus 0.5 s, having slope minus 20 dB per decade and starting from the corner frequency omega equals to 2. So all the four factors have been represented. Now draw the resultant magnitude plot. The resultant magnitude plot will be the sum of all these individual plots. We have individually plotted all the factors of the transfer function on the magnitude plot. Now we are going to sum up all these plots. So first here we have the magnitude as 0, here 20 dBs is the magnitude, here 34 dBs. So 20 plus 34, it will be 54. So our magnitude plot is going to start from the point 54 dBs. Okay. Now slope, here the slope is 0 dBs and here the slope is minus 20 dB per decade up till this omega equals to 1. So up till omega equals to 1, this resultant magnitude plot, it is going to have the slope minus 20 dB per decade. So draw this line. Okay, so this is due to both these factors. This factor is the constant term 50. So this was up till omega equals to 1. Now we have to draw for again proceed this magnitude plot. Here between this omega equals to 1 to omega equals to 2, we have this line and this line. Also we have the factors. This straight lines magnitude plots are due to the factor 1 by s, due to the factor 1 upon 1 plus s, and due to this 34 dBs, that is 50, the constant term factor. So their slopes is going to get added. Due to this 1 by s, the slope is minus 20 dB per decade. Due to this 1 upon 1 plus s, the slope is minus 20 dB per decade. And due to this constant term, the slope is 0 dBs. So these three slopes, they are going to get add up like 0, minus 20, minus 20. So the total slope will be minus 40 dBs per decade. So between this omega equals to 1 to omega equals to 2, the slope will be minus 40 dBs per decade. So draw the slope here. This was minus 20. So minus 40 you have to draw. This slope was minus 20 dB per decade. This slope is minus 40 dB per decade up till omega equals to 2. Now after this omega equals to 2, the slope due to this factor 1 upon 1 plus 0.5 s is also going to get added. So minus 40 plus minus 20. So it will become minus 60 dBs per decade. So minus 60 dB per decade. This was minus 20, minus 40. So minus 60. So this line is minus 60 dBs per decade. So this is our complete Bode plot, magnitude plot. This frequency is omega equals to 1. This frequency is omega equals to 2, this point, and this point is omega equals to 4.45. When you will mark on this board plot, you are going to get here 1, 2, 3, 4. So it is in just middle of this here. So it is 4.45. Okay. So this was the complete magnitude plot. Now for phase plot, we will use the phase table which we have make here. So for omega equals to 0, the phase angle is minus 90 degrees. For omega equals to 0.1, the phase angle is minus 98.6 degrees. So this board plot, it is starting from 0.1. So we will have to take this frequency in the table. So 0.1, the phase angle is minus 98.6 degrees. So minus 90 is here, minus 98 will be somewhat here. So the phase plot is going to start from this point, that is minus 98.6 degrees at the frequency 0.1. So start from here. At omega equals to 1, the phase angle is minus 161.6 degrees. So at omega equals to 1, this is omega equals to 1 line, and at this the phase angle is minus 161.6 degrees. So it is 90. This is minus 90 degrees. This will be between this minus 90 and minus 180. We will have this point. So mark it. It will be somewhat in middle of this. 90, 161 will be here. Now at omega equals to 1.4, the phase angle is minus 179.5 degrees. At omega equals to 1.5, the phase angle is minus 183.2 degrees. At omega equals to 2, the phase angle is minus 198.4 degrees. So draw this angle minus 198.4 degrees at omega equals to 2. Omega equals to 2 is here. So minus 198 will be, it is minus 180. So it will be here. Draw these lines. This is 1. So 0.5 will be here. 0.1, 0.2, 0.3, 0.4, 0.5. At 0.5, the phase angle is minus 130. Minus 130 will be here. Join these lines. Then this is omega equals to 2. Then we have omega equals to 4.5. Also the angle is minus 233 degrees. So here we have minus 180, it is 270. So 233 will be here. We have marked all the points. Now this is our phase plot and this is our magnitude plot. So in our problem, it is asked that we have to sketch the board plot And also we have to calculate the gain margin, phase margin, gain crossover frequency and phase crossover frequency, so that we can make a comment about the stability of the system. Now, this gain margin is what the frequency gain margin will be at minus this, the frequency at which this phase plot is intersecting with the minus 180 degrees line. So here calculate the phase margin. This is the frequency at which the phase plot is intersecting with the minus 180 degrees line. So at this frequency, the difference of the magnitude plot with the 0 dB line is the phase margin. So this is the difference. So this is the gain margin. And the frequency is phase crossover frequency. When we will calculate this frequency through this scale, this phase crossover frequency will come out to be 1.4 radians per second. Now for calculating the phase margin, the frequency at which this magnitude plot is touching this 0 dB line. This is the frequency at which the magnitude plot is touching the 0 dB line. It is the gain crossover frequency. And the phase angle at this point, the margin, the difference between this minus 180 degree line and the phase plot is the phase margin. So this is gain crossover frequency. This is our phase plot, and the difference between the minus 180 degree and the actual phase angle is the phase margin. Because what is the definition of gain margin and phase margin? Gain margin is the additional gain which we will have to add up in the magnitude plot so that the system goes into the verge of instability. So this amount of gain we will have to add up so that the phase plot, the magnitude plot, it is going to be at this 0 dB's line, and this much amount of phase we will have to add so that the system will have comes towards the minus 180 degrees line. So this is the phase margin and this is the gain margin. Gain margin obtained at the frequency, it will become the phase crossover frequency, and the phase margin, the frequency will become gain crossover frequency. So we have sketched the Bode plot of the system, and also we have calculated the gain margin, phase margin, gain crossover frequency and phase crossover frequency. So let's write that what are the values of all these variables. Phase margin, gain margin, phase crossover frequency, gain crossover frequency. So what is the value of all these variables? We have got phase margin is minus 53 degrees, gain margin is minus 27 dBs, phase crossover frequency is 1.4 radians per second, and gain crossover frequency is 4.45 radians per second. So we have calculated all these variables. Now if you observe, the phase margin and the gain margin are negative for this system. Gain margin and phase margin are negative, and if the gain margin and phase margin are negative, then the system is unstable. Okay, so we have commented here about the stability of the system, that the system is unstable because the gain margin and phase margin are coming out to be negative. So whenever we have such type of questions that we have to sketch the Bode plot, what we do, we just replace the S by j omega, obtain the frequency response of the transfer function, then form the tables, obtain the magnitude and the phase equations, and then form the tables for the magnitude plot and for the phase plot, then sketch the Bode plot of the system, and through the Bode plot you can calculate the gain margin, phase margin, and phase crossover frequency, gain crossover frequency. And if they are coming out to be negative, then the system is unstable. If they are coming out to be positive, then the system is stable. And if they are coming out to be zero or they are same, then the system is marginally stable. So this is how we can solve the problems based on Bode plot. I hope this problem is clear to you. Thank you.